So the goal at the end of this video is to understand and get lists of transformations to go from a pre-image to an image. So this is actually not too bad, but this last example here is actually ridiculous. I wrote this example and I was thinking at the time that's going to take a long time to explain. But if we can understand each of these different pre-image to image orders and get a transformations list, then we'll be set. We'll understand transformations completely. This is the hardest part of transformations, by the way. It's not necessarily getting the equation after transformations. That's admittedly a bit easier. This is actually hard because this requires a lot of critical thinking skills and a lot of foresight, I guess is a way to put it as well. Now, example 1, x squared goes to 2 outside of x minus 3 squared plus 1. Now, when we get orders of transformations, the most common order that we use is DRT. You might have heard this before, you might have done transformations beforehand, and you might not understand why we use the order DRT. And the order DRT is used because D and R, so dilations and reflections, they're actually multiplicative transformations. And translation is just an additive transformation. So translation, sorry, is an additive transformation. So what that means is that we're just following the BODMAS order, and that when we follow the BODMAS order, that means that what values we read off are in BODMAS as well. So for example, this first instance here, we have 2 outside of our function, right? So when we apply the dilation first, what happens is that we get x squared becomes 2x squared. And then when we apply our translations, they just go in the slots after that multiplication. So it makes sense to follow the order DRT because that's usually how we make our transformations, and that's how we read off them as well. And it's always good to, if you're unsure with these types of questions, you can apply the same transformations that you got and you see if you get the same image from that same pre-image that they've used in the question. So for the first one, we have x squared becomes 2 outside of x minus 3 squared plus 1. And now this is just an exercise of reading off this image here and seeing what each of the numbers represent. Kind of the same thing that I talked about at the end of the previous video. Each thing in a function is pretty much just a representation of one of the transformations or a combination of them as well. So this 2 here is a pretty standard one. When we have a 2 outside of a function, that usually means a dilation from the x-axis or a dilation in the y direction by that factor. So the first transformation that we have is a dilation by factor 2 from the x-axis. Cool. Now, what sometimes I like to do, and this is what I teach students as well, after you get one of the transformations, just evaluate what the image would be if you only applied that transformation. Because what happens is that when you apply a transformation after that, it just applies to that intermediate, that transform function anyway. So dilation by factor of 2 from the x-axis, if we did that to x squared, we just simply get 2x squared. So I'm just going to do that to the side there. Maybe I won't do it underneath to save space. I'll just do it to the side, and I'll just show you that we end up getting 2x squared after this step here. And then for the transformations after that, we're just going to get, on top of the 2x squared, we're going to have more transformations. So the next one we have is the -3 and the +1. Now we know based on our turning point form that this is a translation in the x direction by 3 units, and it's in the positive x direction as well because it's minus. So it's the opposite sign for x translations. So what we end up getting is a translation by 3 units in the positive x direction. Cool. Now this is the proper way of listing out a transformation as well, or a translation specifically. Translation by 3 units in the positive x direction. Please don't just say right, just say positive x direction. I know it's a bit longer, but you'll get you the full marks because you're being very explicit with the direction that you're stating. Same as the dilation, I didn't specify this before, but dilation by a factor 2 from the x-axis. That's the equivalent of a dilation by factor 2 from in the y direction. So in the y direction is the same as from the x-axis. Either one will get you the marks. Don't say from x, don't say anything like that. Just use the full terminology. This phrasing here is perfect dilation by factor 2 from the x-axis. Now translation by 3 units in the positive x direction. So we end up getting 2 and then x minus 3 squared for that step there. Then the last one is this +1 here. So that is a translation of 1 unit up based on our turning point form. So translation by 1 unit. So this handwriting is really messy, but I just really want to do this fast. in the positive y direction. And obviously all that's going to do is just add a 1 to this equation here, which gives us our final result, which is 2 outside of x minus 3 squared plus 1. So that kind of ticks off what we've done, and it kind of validates everything that we've done too. Now, if you swapped steps 2 and 3, that's fine. It gets you the same answer, because translations can be done at the same time because they're influencing different parts of our equation. So that's perfectly fine. You can do them both at once. Again, they're both additive, so you can interchange them. Same as dilations and reflections as well. Dilations and reflections, they don't, they interfere with each other, but they don't kind of affect our final result. It'll be different if you did the translation, then the dilation, then another translation. That'll get you a completely different result. And we don't want that, and that's why we just stick to the convention DRT for the most part. Cool, sweet. Actually, when I say we stick to DRT for the most part, take the most part with a grain of salt. Most of the time you do follow the order DRT, but personally, I sometimes don't follow that order, and we'll see when it comes to things like this. This step 3 is a really hard question, as I said before, and there's a reason why we don't follow the order DRT for this part of the question here, but we'll cross that bridge when we get to it. We'll stick with question 2 first off, which is x squared becomes 2x minus 6 all squared. Now, at this point, you're probably pretty confident with reading off transformations, and you're also confident with applying them. So what a lot of people would do is they would straight away say, okay, we have a 2 multiplied by the x, therefore we have a dilation by a factor 1/2 from the y-axis, that's perfect, right? We reciprocated the factor, which is awesome because we have a dilation from the y-axis, or it's inside our function. And then we have a translation of 6 units in the positive x direction. And that looks good as well because we have a minus 6 there. We considered that we have an opposite sign for x translations, and that process is so close to being right, but the problem is that we have 2x minus 6 and it's not factorized. So what we need to do is we actually need to factorize this first to become 2 outside of x minus 3, and that's all squared there. Now, what that actually does is it allows us to have our dilation first and then our translations applied after that. So what we've done here is this is expanded, which is perfectly fine. This question's here to deceive you, but what we need to do is factorize it first, and then we follow the order DRT because we want to find our dilation first, which is factorized on the outside, and then we have our translation of 3 units, not 6 units. And we'll actually see when we do our steps and we find our equation after each step that this is right. This will kind of validate what we're thinking. So the first thing we're going to do is apply the dilation. So a dilation by factor 1/2 from the y-axis. From the y-axis is the same as in the x direction. So this would give us, after applying that to x squared, it's going to give us x over 2 all squared. No, sorry. That's going to give us 2x squared. Can't believe I wrote that wrong. Let's rewrite this. So this would give us 2x all squared. Now, the next step would be a translation of 3 units in the positive x direction. So I'm just going to write t for translation. 3 units, positive x direction. Please don't do this when you're actually writing, you're working out. I'm just doing it for shorthand just so we can save a bit of time here on writing. So then what we do when we apply the translation of 3 units in the positive x direction, that's applied to the x by itself. So what we end up getting is 2 outside of x minus 3 all squared, like that. So then when we expand this 2 multiplied by x minus 3, we end up getting the same result here, which is 2x minus 6 all squared. And this will give us the right list of transformations to get our from x squared to 2x minus 6 all squared. Awesome. Keep in mind that this is not the only order of transformations. The same as all of these questions, there's multiple ways of getting the same transformations. So what I've seen a lot of other people do with this type of question is they actually take, let's just move this to the side here. They take this form of the equation, so they have 2 outside of x minus 3 all squared, and they see that you can actually move the 2 to the outside by squaring it. So this is actually the equivalent of 4 outside of x minus 3 all squared. And then what you can say is that you have a dilation by a factor of 4 from the x-axis rather than the y-axis, and then the same translation in the positive x direction. And that'll be a perfectly valid answer as well. It's just a different way of doing the same question, perfectly fine. It's good to understand both. It's not essential to understand both, but it's good to note that there's not always just one list of transformations that get you the same answer. Sweet. So this last question is a hard one, admittedly. Now, the reason why it's difficult is because we have a complex function and we're going to a more basic function. So usually when we have transformations, it's usually applied to the most basic form of a function, or just a function, and then we expect it to get more complex. In this case, it gets less complex. So you can kind of think of it as working backwards to get from a complex function to our most basic function. And it is pretty difficult. If I look at this question, I'm thinking, it's hard to see straight away what transformations would actually get rid of the 3 and then get rid of the 1 and then get rid of whatever's inside the bracket as well to give us our x squared back. Now, what I would say, and this is kind of a callback to what I said at the start of the video, DRT works for most of the time, especially in these forms here, where you go from a basic to a more complicated function, or even if you go from a complex function to a complex function. The problem is, when you're going to a more basic function, sometimes it's harder to use DRT. So what I'm going to do is I'm actually going to work backwards and do TRD. So TRD, I'm going to work backwards to get rid of everything step by step and work backwards to give us our y is equal to x squared back. So I'm just going to specify this at the top here. I'm going to try and use TRD, and I'm actually going to show you why it's a lot easier to use rather than trying to kind of force DRT on ourselves here. Now, I'm kind of working, I wrote these examples and I didn't realize it was going to be this hard, so I'm actually trying to think about how to do it as I'm doing it, but we'll give it our best shot. So the first thing I'm thinking is, okay, I want to get rid of this -1 on this side here, and I also want to get rid of the translation in the x, because I want to get rid of the translations first of all. I'm trying to think about a way to explain it, and I'm just kind of thought of something now. When you have an equation, right, and you're trying to rearrange for something, you follow reverse BODMAS, and a lot of us actually don't think about that. But for example, if you have x minus 3 over 4 is equal to 1. What we're doing is we're essentially following reverse BODMAS, or we're following BODMAS. So what you can see is we multiply the 4 to the other side, and then we move the 3 across. We're essentially just doing the backwards here because we're trying to go backwards. We're trying to go from a complex equation to a basic equation. So what I'm going to do is I'm going to get rid of the translation first of all. So what I'm going to say is just shorthand. We have a translation by 1 unit. Now, right now, we have -1. And essentially what we want is we want it to become like +0 or -0. We just want to have nothing there. So what we need to do is do the backwards of this to get rid of it. So right now it's translated by down, or it's translated downwards by 1 unit. So what we need to do is translate it upwards by 1 unit to get it to 0, or to get it back to baseline, if that makes sense. So what I'm going to say is it's in the positive VE, that's really shorthand, y direction. So what that's done is it's got rid of my -1 on the outside because I've translated upwards, and what I'm left with is 3 outside of 2x minus 4 all squared. Sweet. Now what I'm going to do is I'm going to do exactly the same to my x value. But what I need to do first is factorize it, same as the previous question, to get a good representation of my translation in the x direction. So we're going to do 3 outside of 2 outside of x minus 2 all squared. So then what I can do is I can translate x back in a certain direction by a certain amount, and that'll get rid of the -2 there. So that's my goal for the next step, is to do the next translation, but it's in the x direction rather than the y. Now, again, we want to think about what our goal is. Our goal is to get rid of this -2. So let's think about it, right? Right now, we're translating, or this graph from our kind of basic form is a translation by 2 units in the positive x direction because it's a minus. So what we need to do is we need to add 2 to it, right, to get rid of it. Now, when we have a +2, we know that that's a translation in the negative x direction because we're adding 2. So what we need to do is we need to say a translation, or we need to apply a translation of 2 units in the negative x direction. Again, because that's what's going to +2 there, which is going to get rid of our existing -2. So we're essentially just going the opposite direction of what's already been applied. So then the final equation after this step is going to be 3 outside of 2x all squared, because that got rid of our translation in the x direction. Awesome. That sounds right. I'm pretty sure it is right. Hopefully it is. Hopefully I don't have to re-record this video, because I would like not to, because it's been long up until this point. So let's continue here. There's 2 different ways that we can tackle the next part. The first one is by combining our dilations by expanding this squared out here. That would be an easy cop-out way, but we don't want to do the cop-out way. We want to do the full way, the most complex way, because that provides us with the most learning. But personally, I don't care which one you do on a test. If you do the easy way, I'm going to be proud of you because you save time. But I want to do the more complex way, just to, not to prove a point, but just to show that if you get something like this where you can't simplify it together, this is how you actually do it. Now we can focus on one versus the other. Again, we don't discriminate between the two because they're both dilations, they're both multiplicative, and they're independent of each other for the most part. So what we can do first off is just get rid of this 3. That'll be the easiest one. Now, right now, this is a dilation by a factor of 3. That's what it looks like. So we do the opposite of that, which is a dilation by a factor of 1/3 from the x-axis. And that's going to multiply a 1/3 on the outside, which is going to slash out that 3 on the outside. So what we're going to do is a dilation by a factor of 1/3, and this is going to be from the x-axis. So again, what that's going to do is put a 1/3 on the outside of everything, which is going to get rid of that 3 and just leave us with 2x squared. And then for our last step, what we're going to do is get rid of that 2. Right now, if we just read this from its current form, it looks like a dilation by a factor of 1/2 from the y-axis because we reciprocate our dilation factor for y-axis. So what we need to do is we need to get a 1/2 in there, and that is a dilation by a factor of 2 from the y-axis. So a dilation by a factor of 2 from the y-axis. And what it's going to do is put a 1/2 inside our function, or it's going to replace x with x over 2. So the 2 and the 1/2 will cancel out, and you're just left with x squared, which is equal to x squared, which is our image equation in this case. Awesome, that was actually really hard, but I'm glad we got through it. Hopefully it did make sense. Hopefully you did follow along. The worksheet should be able to kind of refine your knowledge and practice with different types of functions. I know we've used quadratics a lot here, but it's just because it's something that we're used to. Didn't want to complicate it more than we needed to. Just keep in mind that, again, there's 2 things I want to emphasize. One, there's not just a single list of transformations that's correct.